This is the components of quantitative analysis series, an introduction for clinical investigators. This is part 2, data types and parameterization. So when we think about data and models, quantitative models use data. For machines and computers at that level, it's bits, which are zeros and ones that we use to encode the data. But ultimately, when we say data, what we're talking about is how does information correspond to what is represented quantitatively. Ultimately, what we're talking about is how do we represent information with numbers, which is this entity of measurement. So if we think about it for like length, for example, we might measure that in centimeters, where some value of 23 centimeters corresponds to the length of an object. More appropriate to like clinical decisions, for heart failure symptoms, we might measure this in NYHA class, 1 through 4. Here, a value of NYHA class 2 corresponds to the information represented as symptom severity of an individual's heart failure condition. Again, as we get more complex, you start to see that, how the information can be represented in different ways. Mortality, for example, can be represented as the deaths across some population as a percentage, or it can be represented as the probability of death within some time frame, we think of as a rate. So, for example, if I said someone has a 25% 5-year mortality, that's the data that correspond, or the measurement corresponding to the probability of dying within 5 years. Again, that's sort of the information. Again, this is, a challenge. Obviously, if you can't measure it, then you can't represent it with numbers. So when we think about things like health or general well-being, obviously, then, there's no good way to measure that. And ultimately, we can't really use that as data, or we can, think of ways to represent that with data, which is one of the great challenges, I think, with a lot of clinical data modeling. So, coming back to this idea of models as sort of we have our inputs, X producing an output Y through a some model or function. Uh, Again, for both of these, if we're going to use a quantitative model, they have to be represented as data, meaning that they must be measured or measurable. Conceptually, the model is based on information. Again, in our mind, the numbers might say what they are, but ultimately what we're talking about is not what are these numbers representing X and Y mean, but actually what's the information behind them. So what is the conceptual idea linking X to Y? Of course, quantitatively, we're using the data that represents the information. And of course, there's a problem when the data doesn't equal the information that's used in the model, meaning that the data is a poor representation of the information that we're trying to represent. We measure something one way, but it's actually corresponding to a different type of information. This is important in epidemiology in terms of bias or confounding. Data doesn't always, just because you have data doesn't mean that it's actually the information we care about. So when we think about data types, this is sort of like what makes up these variables, or what the inputs or outputs. And so when we think about the inputs, X or predictors, these can be direct measurements, as we sort of talked about, continuous units, things like age, height, systolic blood pressure. Again, the measurement itself is sort of the entity that we're using. Of course, we can also process that to different categories. These can be ordinal, meaning that they have some meaningful relationship across values, such as stages of cancer, or a Likert scale. This is kind of your, kind of scale of 1 to 5. How much do you like flowers? Versus unordered categories, things like categories of movies, clinic locations within a town. Again, these are categories, but they don't have any natural representation. There's no natural order to these categories of movies or kind of clinic locations. And then of course there's the binary and dichotomous. These are your yes, no, 0, 1. Do you have high blood pressure? Yes or no. Do you have coronary artery disease? Yes or no. Um, like the inputs, the outputs also have different data types. Again, thinking about both, quantitative things. Again, these are things we can measure, such as your lifetime in years, your 40-yard dash time, total points scored in a game. These can be categorical, again, as we saw, ordinal, such as the New York Heart Association class. These can be sentiments, such as like if you're doing a text recognition and saying whether someone's happy or sad. And is there an animal in a picture? Image recognition. These are all examples of categorical, whys. This is what we're predicting. And then binary or dichotomous, alive or dead, winner or loser, was the diagnosis of atrial fibrillation applied. Again, so for both the inputs and the outputs, we can basically have different data types based on how we want to measure that data. Now, this idea of how do we represent these inputs, how's the information represented, with data, or how do we determine the data type is something called the parameterization. And this is a really important idea in modeling because, ultimately this is what determines what types of models we can use. For example, for systolic blood pressure, I can measure this in millimeters of mercury as sort of a continuous measure. I can measure this as stages of hypertension, in which case it's sort of an ordinal categorical variable. I can, encode it as diagnostic code for high blood pressure as a yes/no dichotomous variable. Again, it's the same entity, blood pressure, but we're representing it in different ways. This is the parameterization of blood pressure. And importantly, the parameterization determines what type of model you can fit. Again, we won't go into a lot of the details of all the different types of models, but for example, if it's a continuous output, then we can use a regression or a linear regression model. Regression is often applied to machine learning to indicate predicting any continuous outcome, although it's obviously a misnomer because logistic regression doesn't predict that. Categorical outputs, we can use ordinal or multivariate, something called the softmax model. If it's a binary model, then we can a binary parameterization of y, then we can use a logistic regression model, which predicts sort of probability of being a 1 or 0. Importantly, the parameterization should fit the application. Again, keep in mind, continuous measures in general, we think this is closer to the actual measurement, that you're making. And so, they're thought to have more statistical power because there's a broader range of values. In theory, there's less information because you can have different intervals of measurement versus if you dichotomize or categoricalize measures, it's easier to apply, certainly easier to interpret. But again, you might lose information going from saying someone has hypertension based on some dichotomous cutoff versus the actual measured blood pressure. An important consideration, of course, always is the practical consideration. How are we going to get the data? Can I get a continuous measure, or is it easier to just get a category? I think when you're thinking about data, it's important to think of data sort of as a hierarchy. And again, this comes up a lot, nowadays in the era of digital health, where we can get all kinds of levels of data. So, the way I kind of think of this is, there's this idea of data purity, which is going from spam, the most processed, to the most sort of raw, like carrots that you can just eat coming out of the ground. And just as an example, we can look at blood pressure. The raw measurement here is just the sounds you hear. You put a stethoscope or something on an arm, you listen for these cord cuff sounds, that's the raw measure, is what you hear, the actual noise impulses that you're hearing. Of course, our brains do this, a blood pressure cuff does this. We can compute something we measure as the blood pressure, the systolic over diastolic measure. This is sort of, a little less pure than the raw sounds, but you're computing this into a blood pressure. Again, from there, you can start to, process it more. You can make cross-sectional measurements. So you're measuring in an office, that's sort of one setting. This you might measure blood pressure continuously. Now you're getting it to just one. Again, you're losing information between when they, you had a continuous measure and then when they show up in the office. And from there, we start to categorize. We have classes of blood pressure, classes of hypertension. We get the dichotomous diagnosis, hypertension. Again, this is getting more and more processed down to ultimately some billing code. That's sort of the ultimate process. This is sort of taking this diagnosis and categorizing it based on some decision we'll make as far as charges. Again, it's sort of the alternative to this to think about is that, as you move from the most raw data down to the most processed, we're losing information. So, again, Korokov sounds is the rawest data, lots of information here, but again, it may be harder to interpret or harder to measure. The flip side is, as we do this, we're also injecting bias into it. If we're going from continuous, measures to reading in an office, when did they show up in the office? Why did they show up in the office? These categories are obviously biased based on, some cutoff that was selected, and moving on downwards. And so, again, in theory, the most information are sometimes the raw or the closest thing to computing the data, certainly on a 24-hour ambulatory blood pressure cuff. But again, that's at the trade-off with practicality, and can you, it's easier to just go and get a bunch of diagnostic codes about hypertension than it is to go and have people wear 24-hour blood pressure monitors. So just coming back to this idea of data types and parameterization, important to think that, information is measured as data. That's what we're trying to do is measure the information, and we're using the data to represent that. The determination of the type of data that we're, or how we're going to represent that data is called the parameterization. The parameterization determines, what types of models we're going to do. It basically everything flows downstream from there in terms of what we do in terms of models, creating them, evaluating them, subjects that we'll be discussing much more detail. Which parameterization we use is based on a number of things, including how is it measured? Does the measured data match the information meaningfully? Is it biased? Is there a loss gain of information? There's sort of this idea of there's a trade-off if you go from something continuous to something dichotomous. Is that worth it or not? And then, of course, obviously the practical considerations, of how do we, how easy is it to obtain? How is easy is it to store? And ultimately, this is all important because that parameterization determines the types of models that can be created. And certainly when we start to evaluate models, understanding how it was parameterized and all of these issues related to whether that's meaningful or not is a critical part of that evaluation process.